Think forward. Think Research Channel.
We live in a technological age that offers us many ways to investigate the universe we live in. This is the story of one of those ways. It's nighttime at White Sands Missile Range in the middle of the New Mexico desert. Launch Complex 36. In exactly 26 seconds, this 52-foot-tall, two-stage rocket is going to leave the Earth for a little while, about 15 minutes or so. The payload sitting atop this modest launcher is a telescope, a rather special kind of telescope called WISP. Are you ready? Here we go.
6, 5, 4, 3, 2, 1, 0, +1.
Wow, look at that! In a split second, literally, this space-bound telescope has blasted from the pad and right now is racing straight up into the sky at several thousand miles per hour. But wait a second, what kind of telescope needs to ride on a rocket anyway? What does it look like? Why is it called WISP? Whose idea was it to launch it in the first place? And what exactly is it going to do in space when it gets there? Okay, let's back up and start from the beginning. This is Chamberlain Hall at the University of Wisconsin in Madison, more than 1,500 miles from the New Mexico desert. It's the home of the UW Space Astronomy Laboratory. And this is Dr. Ken Nordsick, the original developer of the WISP telescope. And this is WISP.
It's the Wide Field Imaging Survey Polarimeter, or WISP, and sort of named that way because many of the things we look at look kind of wispy. So you always have to have a good acronym.
Funded by NASA, WISP is a space telescope. Unlike standard ground-based optical telescopes, WISP was designed to look out into space from well above the Earth's atmosphere. So why do you put a telescope in space anyway? Walt Harris is also with the Space Astronomy Lab.
What we do is we get beyond the Earth's atmosphere. The Earth's atmosphere is a wonderful thing. We breathe it. It protects us, but it also blocks a great deal of the light that's produced by the sun and other astrophysical targets that we might be interested in. And if we want to do observations in those very specific spectral ranges, we have to get above the Earth's atmosphere to do the observations.
As with any telescope, the main objective is to take a closer look at objects very far away. But the rocket team that designed and constructed this rather exotic telescope has an equally important goal. As they do the science of astronomy, they are at the same time developing and testing the very equipment and methods used for exploration. As a matter of fact, on board the flight we're about to witness is a revolutionary device created right here at the Space Astronomy Lab. It's called the Star Tracker 5000, a very sophisticated instrument with potential application for the entire space program. More on the ST-5000 in a bit, but right now back to WISP. It's a suborbital launch, which means WISP doesn't actually circle the Earth like, say, the Hubble Space Telescope. The rocket travels straight up. The payload separates from the rocket, does all of its work in the vacuum of space, and then comes straight down to Earth again. For most of his career, Dr. Nordsick has devoted his explorations to a special field of astronomy.
The technique that I've specialized in is called polarimetry, which is a property of light that is difficult for people to understand because our eyes actually don't sense it. Light is a vibration, an electromagnetic vibration, and in addition to the frequency of the vibration, which is the color, it also has a direction, and the direction is the polarization.
WISP is a special kind of telescope. It's an ultraviolet polarimeter. It's designed to see a range of the electromagnetic spectrum that's invisible to our eyes.
Well, a spectral range is basically what is defined scientifically as a group of wavelengths or colors. We call the visible those group of wavelengths that we can see with the human eye. Other groups of wavelengths, spectral ranges might include the ultraviolet, X-ray, infrared, radio, microwave. All of those are groupings of wavelengths of light that are classified by their energy characteristics and their color.
Of course, there is more than one way to get a telescope above the Earth's atmosphere.
Well, the sounding rocket experiment, I think, offers three primary advantages. The first is that it's not very expensive. It costs up to 50 to 100 times less to launch a sounding rocket than it does to launch a satellite. The second area in which sounding rockets are useful is that you're able to test new types of experiments and new types of technology that you would never risk on a $50 million satellite. And the third thing is that it allows you to upgrade your experiment in response to your observations. If you perform an observation from a satellite and realize that the instrumentation is not what you need to do the observation, there's nothing you can do.
You make it work, you figure out what to look at, and then you have an instrument that you know how to build, you know it will work, and you can spend the money to make it into an orbiting instrument.
Satellites typically require many years of planning. A sounding rocket experiment can be put together, particularly if the experiment exists, within a few months if you're ready to go.
As with most things, though, the advantages of using small suborbital rockets, also known as sounding rockets, comes with a set of challenges.
Oh, well, there are a lot of limitations in terms of what you're going to be able to do in a sounding rocket. A typical sounding rocket is only a 17-inch diameter skin section in which you have to house, in our case, a telescope. A 17-inch telescope is a lot smaller than the type of telescopes that you see on the top of mountains. So the number of photons that we can count with our experiment is actually quite a bit limited compared to a ground-based observatory. We also get only a very short amount of time above the atmosphere in which to do our observations, typically 5 or 6 minutes, for which we have spent a year or 2 years of our lives to get to it.
It's got to be more automated the less hands-on opportunity you have. With an airplane, you can operate an instrument in an airplane just like you do on the ground. But once you get into a suborbital rocket or into an orbital mission, those instruments can't be touched, and they have to be automated to some extent.
As you can see, everything about the payload is carefully designed and meticulously constructed in a very solid and sturdy manner. That's because the rigors of a rocket launch are indeed extreme. Okay, the WISP instrument is now fully constructed and ready to go, right? Well, not yet.
Well, assuming that you've built your experiment and you're ready to fly your experiment and you've been working with NASA to develop how you're going to communicate between NASA's equipment and yours, the final step is for you to go out and integrate with the NASA equipment and to do test and engineering on the completed experiment to determine that it will survive launch and function normally as everyone is expecting it to. That requires, in our case, for us to go out to the White Sands Missile Range, to a facility where they have all the test equipment that we need.
This is White Sands Missile Range in southern New Mexico. Established in 1945, the range spans more than 2 million acres. In fact, this is the site of America's very first major launch facility. Some of the very first rockets were tested here, including Wernher von Braun's V-2 rocket, which was brought here after World War II with a cadre of German rocket scientists. The WISP Space Telescope arrives here by truck and is first delivered to the Vehicle Assembly Building. Here, the instrument is physically attached or mated with the other systems that make up the payload. This is an extremely exacting process conducted with great care by rocket professionals.
We go together with NASA's equipment. We go through several hair-pulling days of finding out that one group thought one thing was going to happen and another group thought a different thing was going to happen, and wires are pulled and crossed over and everything gets put back together so that it will work. And then we do what is called a sequence test. We basically pretend we're flying, and we run all of the experiments and all of the equipment in the exact sequence that it will happen during flight. And assuming we pass that test, then we go into the very hardcore environmental testing. We will take the entire experiment and we'll put it on something we call a shake table that subjects it to a tremendous vibrational load that is somewhat similar to what it will see in flight. And when they're done with that test, and some others where they spin balance it to determine that it is properly aligned so that it'll go straight up as opposed to some other place, where they've measured how weight is distributed in it, they give it back to us and we do the sequence test again. And if it passes that second sequence test, then we are declared ready for flight.
Even then, there are no guarantees, as we shall see. Across the scrub desert of this, the southern part of the missile range, several launch pads are spread out in a line from west to east. This is Launch Complex 36. It's just a mile or so from the vehicle assembly building. Here stands a heavily reinforced concrete blockhouse. It's the control center for the flight. And of course, the launch pad itself, a mere 50 yards away. This is the next destination of our fully integrated payload on its way toward an appointment with space. As we've seen, the payload is made up of the telescope experiment itself, plus the systems that make it work in space. We see here the WISP telescope and its electronics, the telemetry section, which communicates from space to ground. The boost phase guidance system helps control the rocket in the early stages of flight. The attitude control system actually points the telescope once in space. And of course, the recovery system and parachute to return the telescope safely to Earth. Once all of the system tests are completed, the payload components are carefully bolted together and prepared for a trip to the launch pad.
What they do at that point is they put it on a big cart and they wheel it out to a launch rail, which is a 50-foot extendable boom that they have already mounted the rocket that you're going to fly onto, and they basically bolt your experiment to the front of that rocket.
In this case, the launcher is a two-stage vehicle called a Black Brant 9. Both stages contain solid fuel propellant, much like the boosters on the Space Shuttle. The rocket will remain in a horizontal position until just before launch. That makes it much easier to perform pre-launch maintenance. The entire stack is 52 feet long and weighs in at 4,600 pounds, including the 860-pound WISP payload. Dr. Nordsick gives us a closer look.
The experiment part of the payload went from there to there. And that's the telescope part of the payload. And that is the telemetry section. You can see the antennas. This is the S19 section. That's the boost phase guidance. This is the ACS, attitude control system. This is the recovery system and nose cone. So the parachute goes in there. That's the door of the experiment. We actually don't look out the top. We look out the side. So this thing at plus 75 seconds or something like that opens out like this, and our view is out to that in that direction.
Back in the blockhouse, all systems are readied for launch. The blockhouse is divided into two sections, one for the launch control team, one for the payload operations team, which of course includes the science team, led by the principal investigator, or PI. That's the astronomer-scientist who has formed the science goals for the mission, and then defined the type of instrumentation needed to meet those goals. Actually, it can be the other way around. The PI forms an idea for, say, a new way to look at polarized light. Then he envisions the technology needed to do it. The actual astronomical observation becomes, in effect, secondary to the development of the new instrumentation. At any rate, the target for this mission is an area within our own Milky Way galaxy called UVX7. That's astronomy talk for designating the seventh target of an ultraviolet experiment that was actually conducted on an earlier space shuttle mission.
It's a bright place, it's a place where they've looked, and it's a place where we see both infrared and visible diffuse light. So it seemed to be the best shot we have at getting the UV component.
During the mission, Ken Nordsick will watch it all unfold right here at his science station.
The first interesting thing is that we will get an on-target signal, and I will be able to tell from here that we've gotten the on-target signal. So I'll probably say, on target. And then after that, we'll get our first image here of the UV diffuse background, if it all is working. So that's the exciting part, because we'll be watching for it and saying, oh, that looks like what we expected, or it doesn't look like what we expected.
The next day is one of systems checks and assurances that all is well for this evening's launch.
Well, pretty much you've done all the things that you need to do in order to get ready for the launch, particularly from an experimenter's perspective. You're ready to go, your experiment is working. The hardest part about the night of a launch is in waiting for the launch to actually happen. You have to disconnect all of your support equipment. You have to sit there and wait while they arm the rocket. All during this time, you sit and you look at the meters that are gauging how your experiment is performing, and you just hope that nothing breaks.
But as the launch team anticipates the upcoming mission, indeed, a problem has emerged. The computer monitoring the systems aboard the payload indicates that a small air pressure leak has developed inside the telescope. If the system can maintain a certain minimum pressure for the duration of the flight, then everything should be fine.
It could be that we're fine. It could be we don't have a problem at all. That we go ahead and we run this, it'll do the same thing again. Or it could be a failing component that worked this time, and the next time we try it, it'll fail completely. Ideally, I would have liked to have had this happen yesterday when we ran the timeline, so we could have come in today and characterized this particular behavior pattern, as opposed to doing it an hour and a half before launch.
So it's out to the pad to check out the actual hardware and repressurize the system. Kurt Janig is the systems engineer for the science team. He removes an access plate, attaches a line from a supply tank, and puts a wrench to it. This is real, hands-on rocket science. As Kurt finishes up out at the pad, back in the blockhouse, the question now is go or no go?
Well, we put a 20-minute hold on the launch that it turns out we won't need. We've discovered that we had this problem for at least one day, possibly longer. We reran the flight timeline from yesterday and that we ran last night, and we noticed exactly the same effect. The choice that we're presented with is whether we go home. And at this point, because we are looking at a mechanical problem that we do understand, and if it behaves as it does, it won't fail in flight. To the extent that we won't be able to get our data. And so right now our decision is that we're just going to go.
We are go for launch. The shelter is rolled back to expose the rocket. The launch rail motors are activated, and the entire vehicle is carefully pivoted to the vertical. A space telescope mounted on a rocket, ready for flight. The hours have turned to minutes.
We began our sequence of events a minute before launch. We began doing housekeeping measurements. We look at calibration lamps. We do background measurements on our detector. We test mechanisms to confirm that they're working.
Let's watch and listen for the final minute before this bird takes flight.
Mark, T-minus 60.
Go. Experiment go.
Minus 5.
There's a lot of superstition and finger crossing attached to the night of a rocket launch. You pace the floors and you wait, and you hope everything works. And as they count down, you continue to do your diagnostics.
Minus 40. 35. Minus 30. 25. Minus 20. 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1.
Wow, it's gone.
7, 8, 9, 10, 11, 12, 13, 14.
At the moment of launch, there's a pretty good release. At least I've always felt that way.
The first stage, the Terrier booster, will burn for just 6.2 seconds. The Black Brant ignites and continues for a 32.4-second burn as the Terrier simply falls back to Earth. At second stage burnout, the rocket is traveling at 5,300 miles per hour. It's on its way to a maximum altitude of 220 miles.
When we get beyond the stage where the rockets are burning, when the payload is just floating in space, during that portion of the experiment, the attitude control system is determining where it is in the universe and pointing to various stars that it knows about in the sky, and then moving over to where we're going to be looking.
In the sounding rocket program, one of the most difficult things is pointing. Each astronomical mission has to go through a fairly long and risky set of maneuvers to figure out where it is. So we actually had a reason to try to get around this problem.
That brings us back to the Star Tracker 5000. Developed right here at the UW Space Astronomy Lab, the ST-5000 is an innovation with implications far beyond this particular space experiment. It represents yet another major advantage in using small suborbital rockets for science: the opportunity to design, develop, and flight test new or enhanced technologies for use in space. Jeff Percival leads the team responsible for designing, building, and testing the ST-5000.
And so that's what we had here. We had the sort of a confluence of things. We had the interest and desire to build the Star Tracker. We also had a flight opportunity, which we took advantage of.
There are new technologies, basically solid-state camera technologies, by which you can build a Star Tracker that is much better than the sounding rocket Star Tracker and much more sensitive and much cheaper. So basically we're in the position of a university suggesting that NASA should develop this new device.
Plus, there's an added bonus.
We have a value-added kind of thing. What we put in the Star Tracker is the ability to send down the images that it's looking at, which other Star Trackers don't really do. Now that's important to NASA.
Tonight, though, the telescope payload relies on the original equipment and is just now locking in on the region of deep space that contains our target, UVX7.
At that time, and only at that time, our experiment door will open, and then our telescope will begin to look at the target that we're looking at.
The WISP telescope begins its task. Several measurements of UVX7 are acquired and then sent down to the ground by radio telemetry. The focus now is on data acquisition. Scientific analysis comes later, back home.
All right, good. We're right. That means we're there. Data coming. And there we are. Ooh, what is that?
Our rockets are completely controlled by pre-programmed sequences. Literally, all we can do is look at the meters and look at the pictures and see what they show us.
Target UVX7 proves to be an interesting one. Dr. Nordsick compares what he sees now with the drawings he prepared earlier. The rocket teams continue to monitor spacecraft systems.
10 minutes after flight, your science is done.
The telescope door closes. All onboard systems are put into re-entry mode. For the entire flight, the payload has continued to move along a ballistic trajectory defined at launch. Like a bullet shot straight up into the air, that trajectory now returns the WISP telescope down through the atmosphere toward an impact with the desert floor at White Sands, just a few tens of miles from where it was launched.
Parachute opens, a beacon turns on, NASA finds out where that rocket is going. It comes down into a field somewhere, something like 50 miles from the launch site. And the following morning, at about 6 in the morning, we get an Army surplus helicopter that takes us over to pick it up.
For the rocket team, this is a time of guarded anticipation. They're naturally anxious to find out how the payload survived the flight. This mission is over. All that remains is to carefully pack up the payload and head for home to evaluate the performance of the instruments, examine and interpret the science data, and plan for the next flight. The WISP Space Telescope has observed several objects in and around our galaxy. From comets like Hale-Bopp to the Pleiades Nebula and the Large Magellanic Cloud. Small snapshots in an incredibly immense universe. In many ways, that's what astronomy is all about. Looking all over the sky and making small pictures in order to create a much larger picture. It's the ideas of scientists and astronomers like Ken Nordsick, Walt Harris, Jeff Percival, and many others who contribute to the exploration of nature we call science. The names will change, the missions will change, they always have. But along the way, science expands, and the quest for knowledge continues.